I'm now going to attempt to do some examples. Again, the examples are not going to be done in complete detail, but I want you to think about going from words to a free body diagram to equations. Unlike normal, I'm actually going to show you the text, and these are of course book problems, but I want to talk you through how they work. Again, this might help even if you have access to the book to hear me explain it and then read how the book did it, since especially I'm going to go through part by part. If you don't have access to the book, then I'm going to hopefully be presenting this enough for you to understand at least the beginning of the problem. So first we have that a 1,500 kilogram car is pulled by a tow truck. So the first thing is it sounds like this might be my object, right? Especially since I see it referred to later. And so this 1,500 kilograms is my mass. Okay, it is pulled by a tow truck. The tension in the tow rope is 2,500 newtons, and a 200 Newton friction force opposes the motion. Now, we haven't learned about friction yet. That's going to be in next week's topics. However, at this point, you're not being told so much that you have to calculate friction yourself. You're told the magnitude of the friction force, so that's completely fair game right now. The question is, if the car starts from rest, what is its speed after 5 seconds? Okay, so what else do we see here? I see that there's going to be two forces. One force is this. So I have a tension force. The magnitude of that is 2,500 newtons. And then I have a friction force. And we're going to say in this case, since it's moving, that this needs to be kinetic friction, and that this equals 200 newtons. And the question is, what is its speed after 5 seconds? Note that this is now a velocity and a time. And so what you should see is that here we need to do something with kinematics. Well, the forces tell us that this isn't purely a kinematics problem. So we need to first figure out what's happening with forces and acceleration, and then we can relate the acceleration to speed and time. So what would you do next? What you hopefully would do is draw a picture, label your variables, do some simplification and some modeling, and then draw your additional representations. In this case, you definitely want there to be a free body diagram, and you probably want there to be some sort of sketch thinking about the motion of it explicitly. Remember that motion doesn't appear on a free body diagram, and that would be one reason why a free body diagram here is not enough. You definitely need it, but you want a second representation as well. So before I actually show you the picture, what modeling do we think might need to happen? Well, again, we have two force models, and I see force appearing here. So is it in equilibrium? Well, probably not. First, we see that it doesn't seem like the forces are canceling each other. Second, we say that it starts from rest, and that it's going to have a speed after 5 seconds. That means its velocity is changing. So we definitely don't want to use an equilibrium model for this. So the other model we have is a constant force model. So that means that we want, that we want to say that that tension force is always constant, the friction force is always constant. In the real world, those probably vary a little bit as the car goes over bumps and whatnot, but we don't want to worry about that here. We need to simplify it enough that we can solve it. So the model we're using is that constant force model. Instead of me attempting to draw everything on the computer screen, I'm going to use the picture available in the book. And note that the book has actually now done 4 different representations. First, the book has done a sketch, which is focused on the kinematics, that we have our initial position, we have our final position. We're thinking about the position, the velocity, and the time, and the fact that there's a constant acceleration between the two of them. We've also here defined our coordinate that we're interested in, x. So to the right is positive x. And the book has made its nice table of the knowns and the thing we're trying to find. But that is not good enough. What you then might want to do is a motion diagram. Now, I would say that a motion diagram is maybe not necessary. However, you definitely want to remember that you have an acceleration to the right, that it's speeding up. What you do definitely want to think about is now your forces. Now, the book always draws this sketch of identifying the forces. I would encourage you to do that until you are a master at forces. And then we have our very important free body diagram. Now, there's something I want to highlight. The book told us about two forces, tension, which we've assumed is pulling to the right. Now, the book did not necessarily say it's being pulled to the right. However, you were told that the frictional force is opposing the motion. So you could invert the entire problem. You could have the car moving to the left with the tension to the left and the friction to the right. You could just basically flip this in a mirror and nothing will change. It doesn't matter if the car is being pulled to the east or to the west. So be careful. You have to be ready to make some choices yourself, but you want to verify that the choices you've made haven't drastically changed the problem. Now, the next thing to realize, and this is why you probably want to draw this picture, is that the car is on a surface. Why does that matter? It means there's a normal force. Oh, the book didn't tell you what the normal force was. The book also didn't tell you that there's a gravitational force, but the car's on Earth, so there is. So again, when you go to draw a free body diagram, you should label every single force, not just the forces that you think matter. So that's why you might want to draw explicitly this picture and identify your forces. Now, based on the fact that the tension force is larger than the frictional force, you can infer that F net is going to the right, and that's good because that also agreed with how you drew your motion diagram and your sketch. So we have an F net to the right, we have an acceleration to the right. So what is going to happen next? At this point, we are ready to do a calculation. Now, I am going to do this out in excruciating detail to really try to drive home what the steps are. Now, the problem is I don't have enough space for you to see this lovely visualization, which is oh so important, and to actually see the calculation. So if you are learning this for the first time, I would encourage you to either open the book so you can see this in front of you, or potentially do a quick sketch of this so that you have this to refer to. Again, having this visualization is key to doing the problem. For the sake of keeping my handwriting as legible as possible, I've typed in the math rather than writing it out, but I'm going to try to go slowly through it. So the first thing we're going to be doing is using Newton's second law. And remember, you want to do this in components. A common mistake is to mix all of your forces together. That's a terrible idea. So we have our x components and we have our y components. And again, on the picture, we labeled what direction was x and what direction was y. Next, you want to only deal with your x components when you have the x equation and only deal with your y components when you have the y equation. So you have the x components of each of the four forces. Now, some of these are going to be 0. That's okay. But note that you then get your x component of acceleration here. So that's super important. Again, please make sure that every single thing has an x subscript, and that's one reason to be careful with your subscripts. So you do that for x, you do that for y. Then what? Now we see what's 0. So in the x direction, we had tension, which was to the right, so it's positive, and the frictional force was to the left, so that's negative. And I've dropped the subscripts to represent the entire magnitude, because my tension and my frictional forces were purely an x. In the y direction, I had the normal force up, so again, this represents the entire magnitude of that force, and I had my gravitational force down. So it's negative because it's down, and this is now a magnitude. So again, be a little bit careful about thinking about components versus magnitudes versus forces and directions. Be very clear in your notation and be very careful. So now what? Now we use the fact that we can simplify this down and get our acceleration in x. Why are we trying to do that? The whole point of the question was to figure out something about speed. And remember that if this is a kinematics question about speed or position or time, that we need to have acceleration, because forces shouldn't show up in kinematics equations, but the acceleration does. So all I've done is solve for acceleration by dividing m out. Okay. What about in y? Now I can do the same thing in y, and note now that this must equal 0. Why is that? Well, we had our surface and we had our car on it, right? And if we say that up is y and sideways was x, is our car accelerating in y? Is it jumping off the road? No. It can accelerate to the right or accelerate left. Cars frequently do that, but cars rarely leap up into the air. So because of this, we can say that the acceleration in y is 0. This is not saying that the car is in equilibrium, simply that it is not accelerating in the y direction. So then what? Well, note that what we could do here is then actually make some statements about the normal force and gravitational force, but we don't need to, right? In this question, it didn't matter. And so we just go back to x, right? So we go back here, we plug in our values. You were told what each of these three values were, you do the math, and you get this value. This is now your acceleration in x. Okay? I'm not going to do the very last step, which is actually finding what the speed is after 5 seconds. But obviously now you have an acceleration and you have a time and you know it starts from rest, so that final step is fairly straightforward. But again, the important thing here is actually going through this step and drawing your free body diagram correctly. Even though we don't need to use what happens in y, you have done the physics incorrectly if you have completely ignored those forces.